Hey everybody, it's Ribley back again. Okay, now we're going to talk about the limit of a function. This is the mathematical mechanism by which we can solve that tangent problem, that slope of the tangent line. Now, I've got a little graph here that we're going to talk about in a sec, but before we get crazy, I want to talk about some nomenclature, the way in which we the way in which we write this and refer to it, okay? And there's a few things that we're going to talk about that we're going to get a little crazy with. All right, first things first. I'm going to write this limit. I'm going to write this guy right here. And I want to make sure that you understand how to say this. The way in which this is said is the limit as x approaches a of f of x equals L. Now, this assumes something big. This assumes that a limit exists, all right? Which in this case it does, and we'll explain that in just a sec. Okay, but I want to make sure that we understand how to say it first. Limit as x approaches a of f of x equals L. Some people will say the limit of f of x as x approaches a equals L if the limit exists. All right, so what I'm saying here is it assumes that the limit exists. Okay, now let's take that and let's get some practical experience with this guy. All right, with what I'm talking about. Okay, now hopefully most of you remember this from pre-calc. All right, but let's determine how to determine graphically whether or not a limit exists of a function at a point. It's very, very simple. I call it the dental floss method. Okay, here's how it works. What we're trying to determine by what I wrote right here is whether or not the limit as x approaches a of f of x, that's this guy, that's this curve, is actually equal to L. And I'm just going to call this L for a second. All right, now this dental floss method of which I speak is, what you're doing is, you're taking a piece of dental floss and you are draping it across A. I want to be very clear here. You do not care what happens at A. You only care about what happens arbitrarily close to A. So it's as though if my fingers, I can't show you my fingers on here, unfortunately, but if my fingers get closer and closer to A from both sides, I approach A from both sides, and then I cruise up to the curve and I actually put my fingers on the curve. If my fingers head for the same value, whoop, whoop, if my fingers head for the same value, then the limit as x approaches a of f of x does indeed, in this case, equal L. Because notice, my fingers are headed for a value. What's that value equal? If I cruise over to f of x, I get L. But Ripley, you may say, I got this value up here. It's what? I don't care. It's dental floss. As far as the limit is concerned, as far as the limit is concerned, we don't care what happens at A. We only care what happens arbitrarily close to A. So let's look for just a second at the limit as x approaches B of f of x. All right, now drape, drape, drape. As I get closer and closer to B, from a graphical standpoint, I don't really even care about what's happening down here on the x-axis. I only care about what's happening on the curve. My left finger is headed here. My right finger is headed here. They're not headed to the same spot. Guess what? This does not exist. Limit doesn't exist. Now we're going to talk a little bit about different ways that limits cannot exist, which will make you a little bit nuts, but that's okay. All right, so I know that the limit as x approaches a of f of x equals L, because again, by dental floss method, my fingers are headed for the same place. If I didn't have the dental floss there, you would think that they would touch, but they don't, because I get this little point up here that bebops up here. Now, for B, I'm just screwed. My left finger and my right finger don't head for the same value. So it's super easy to determine that way. Now, that takes care of the overall idea of a limit, okay? However, that said, there's something called a one-sided limit. A one-sided limit. And this takes a little bit of nomenclature as well. In the one-sided limit, what we'd say is, let me change colors. What we're going to do is we're going to approach the value on the x-axis from one side or the other. For example, just for giggles, let's make this be L2 and this guy be L3, okay? Now, I'm going to take the limit as x approaches b. Now, I'm going to do a little superscript here, All right, I'm going to approach b from the negative side. Now, that can be confusing because students will think, wait, does that mean just from the negative numbers? No, 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 no. It just means from the left side of the number, in this case, b. So I'm only going to approach b from the left-hand side, or the negative side of b, as if we were putting b at 0. Now, that can get confusing, so sort of disregard what I just said. Just remember, from the negative side means from the left-hand side of the x value there. All right, so limit as x approaches b from the negative side of f of x. Now, same thing, I'm just gonna, I still have my piece of dental floss. I don't care what happens at b, only arbitrarily close to b. Well, here we go. Okay, left side, this is the right side, this is the left side, so I'm gonna approach, whoop, from the left, and what do I get? I get L2. That's easy enough. Now, similarly, this is called a left-handed limit. This is left-handed. Easy enough, right? Now, similarly, let's change colors. We'll call this L3. Up here, if I take the limit as x approaches b from the positive side of f of x. Now, again, positive doesn't mean positive numbers. It means the right-hand side. Okay? So I'm approaching from the right, which means up on the curve, I'm approaching from the right. Don't care about the left-hand side. Still got my dental floss draped over the top of this thing. Do not care. Should be relatively obvious that this guy is going to L3. Nothing to it, right? This is called the right-handed limit. Right-handed limit. Okay? Now, you may say to yourself, now, wait, Ripley, back here, when we were doing this thing in black, we knew that the limit as x approached, I guess we were doing it in blue, weren't we? We knew that the limit as x approached a of f of x equaled L. This is my black L right here. Whoop, this guy right here. Okay? Now, think about, now that we have these left and right-handed limits, and it kind of feeds right into the idea of putting your fingers on the curve, and as I approach from the left and I approach from the right, I head for the same value. So hopefully everybody agrees that another way to write the limit as x approaches a, which is a little more mathematically robust, as x approaches a of f of x equals L. This is true if and only if the limit as x approaches a from the positive side of f of x equals the limit as x approaches a from the negative side of f of x equals L. In other words, these guys both go to the same place as this guy. All right? Now, that's an interesting way to define a limit. And it's, like I said, it's a little bit more mathematically robust. All right. Now, one thing that I want to show you, all right, I'm going to need to pull it up on the graphing calculator because it's a very interesting function. All right, so I'm going to meet you back here in just a sec, and we'll talk about this thing on the graphing calculator. So I'll see you in just a sec. Okay, so the vast majority of all limits you're going to take are going to be really simple, but there's a couple of tricky ones that are difficult to deal with. One of which, excuse me, let me back up, but which you are definitely going to have to know. You're going to memorize these because they're super helpful down the road. One of which is sine of x over x. All right, now we're going to look at what sine of x over x looks like in just a sec. However, I want to make sure that we understand something fully. If I plug in at 0, if I plug 0 into sine x over x, it should be obvious that I get 0 over 0, which is undefined. All right, this guy does not exist. Okay, in other words, this function does not exist at 0. It in no way exists at 0. All right, so hopefully I'm being very clear on that. However, look at the function. Whoops, that's not the one I wanted. Look at the function. That's the one I wanted. I just put in y equals sine x over x. If you look at my window really quickly, I went from -2 to 2 on the min and max, and I made sure that I was in radian mode. There's my radian. All right, so let's go back to the graph. There it is. Now look, let's use our little finger thingy-dingy. All right, sine x over x looks just like this. It's odd, right? It's an odd it's odd. It's an even function, right? Symmetric with respect to the y-axis, which makes sense. F of negative x. Sine is odd. X is odd. They cancel out the negatives and you end up with the evens. Now look though, if I trace my fingers along from the left-hand side of 0 and the right-hand side of 0, they head for the same value. Now, what if something crazy happened in here, like on a micro scale? Well, let's not panic. Let's zoom in just a sec. Let's zoom in, and let's see, where's my dot? Anybody see my dot? Oh, it's up there. I wanna move it up a little bit. Come on, you. Whoa, I don't know what just happened. Let's move that sucker up. I want you to see this. And let's see if I get any janky behavior. Now we'll hit enter. No janky behavior. That's cool. That's kind of nice, right? And I can look at this limit and be like, oh, okay. It appears that both of these guys head for 1. So it appears, and you would be correct in assuming, that the limit as x approaches 0 of sine of x over x equals 1. Now, that's counterintuitive, and it's also, in absence of something called L'Hopital's, it's relatively difficult to prove this. It's not easy to prove this. It's a nasty geometric proof. However, you're going to want to memorize this. You're going to want it in your back pocket because it's super, super helpful. Okay? All right. Now, there's another I want to show you another way to determine this numerically. So remember, it's kind of the 3 posts of calculus. We want to be able to do calculus graphically, we want to be able to do it numerically, and we want to be able to do it algebraically. The problem is, algebraically, we're stuck. We're completely stuck if I try to do it algebraically, because there's nothing I can do algebra on. Graphically, we liked it. It appears that it heads for 1. Now let's do it numerically. So if I look at, I'm going to look at my table over here. Let's set my table. All right, my table start, I don't want to start, well, I can start it at 1, right? Change in table is 1, but let's go down and do the change in table of 0.01, all right? And then we'll go to second table and take a gander at this thing. All right, notice I get my error at 0, right? You agree? All right, so, but if I approach from the right-hand side, notice 0.06, 0.05, 0.04, 0.03, right? I'm approaching from the right. At 0, I get an arrow. It's undefined. But this guy is clearly headed for 1, right? 0.994, 0.995, heading for 1. Now, let's see. I think if I toggle up, yeah, look at that. I love myself right now. If I toggle up, now these would represent that numerical approach from the left. Again, I appear to be heading for 1. So this is a way to look at the problem numerically as opposed to graphically or algebraically. Now, hopefully everybody knows how to set the table on their calculator. If they don't, they need to talk to their instructor, and they need to talk to me, and we can get this thing figured out. If I look at it from here, again, look at 0. This is where we're taking the limit, right? Clearly an error. The function is not defined as 0. This would be the left-hand approach. This would be the right-hand approach. They appear to be heading for the same value, and indeed, that value appears to be 1. Again, a counterintuitive result, but the mathematical result nonetheless. Okay, one more thing that I want to talk to you about, and then we will be done with this section. All right, and it deals with asymptotic behavior, okay? But we're going to take this slow. We're only going to talk about vertical asymptotes, all right? Vertical asymptotes. Asymptotes. All right, now, let's go to a function, our good friend, y equals 1 over x, that we've dealt with since algebra 2, right? So I know what this kid looks like. Looks terribly drawn. It looks like that. And we're going to define horizontal asymptotes in a later section. But for now, we're just going to do this with vertical asymptotes. Okay, or excuse me, with 1 over x. What the heck is wrong with me? And vertical asymptotes. Okay, now, notice, hopefully, by now, you realize that the limit as x approaches 0 of 1 over x does not exist. It ain't there, because my left hand is heading for negative infinity, my right hand is headed for positive infinity. Even if they were headed for the same infinities, the limit wouldn't exist. Do we agree with that? Okay, the limit doesn't exist because there's no such thing as infinity. I can't get there. However, notice that the limit as x approaches 0 from the positive side, now we're getting fancy, of 1 over x is equal to positive infinity. Also, the limit as x approaches 0 from the negative side of 1 over x x, I keep doing that, is equal to negative infinity. We know from past experience that x equals 0, which is the y-axis, that x equals 0 is a vertical asymptote for 1 over x. Now, the cool thing is we now have a rule for determining vertical asymptotes. We now have a rule. It says this: if either the limit as, now I'm going to get really ugly. You know what, I'm going to lose that either. And I'm going to make some compact notation that's it might freak you out just a little bit, but watch, I'll show you. If the limit as x approaches a from either the positive or the negative side of f of x equals either positive or negative infinity, then this implies that x equals a is a vertical asymptote. It makes sense, right? If I'm headed for a value, in this case I'm headed for 0, and whoo, off I take, then I've got myself a vertical asymptote. Now, some weird stuff can happen here. I'm only going to take a couple minutes and go over this with you, but let's still have a discussion. Let's say that I have a function that looks like this. And here's x equals a, and my function goes, here's my function, you ready? Uh-oh, I don't know what just happened there. Like that, and then I've got this point, and I'm going to let this be L. And this is f of x. Okay? Now, watch. As far as we know, hitherto, we know that vertical asymptotes, we're not supposed to be able to cross them, right? Functions don't pass over them. And we may have it planted in our brain that functions are not even allowed to exist on vertical asymptotes. Well, kids, that's not true. And here's why. If I take the limit, this is supposed to be a, if I take the limit as x approaches a from the positive side of f of x, hopefully with my horribly drawn function here, you'll see that I get infinity. Now, according to this right here, boom, right there, that tells me immediately that this implies, whoa, what's going on there? That's crazy. This implies that x equals a is a vertical asymptote. I get that for nothing. I wonder if I can get rid of that. That's weird. No, looks like I'm stuck with it for whatever reason. I don't really care. However, look, the limit as x approaches a from the negative side of f of x, in this case, appears to be L. Now, you guys, that doesn't negate the fact that x equals a is a vertical asymptote. So, in other words, I am allowed to head for these crazy little values, right? I'm allowed to have a limit. Heck, I'm even allowed to have the function be defined at that value and still have a vertical asymptote at that value of x, I should probably say, right? That can be a little bit confusing, but at the end of the day, don't panic. Just say, hey, when I approach from the left or if I approach from the right, if at either one of those or both of them, I end up with the limit equaling a positive or negative infinity, guess what? I have a vertical asymptote. Now, there's a bit of a trick here that we got to be really careful of, a little trap, if you will. Let's deal with f of x equal, that's a little weird to write with, equals 1 over x squared. Now, hopefully in your brain, you can see this as like this, okay, and like this, okay. If I take the limit as x approaches 0, right here's 0, as x approaches 0, of 1 over x squared. Now, you are allowed to say that since the limit as x approaches 0 from the right of 1 over x squared equals the limit as x approaches 0 from the left of 1 over x squared equals positive infinity, which implies that x equals 0 is a vertical asymptote, right? Because the limit from the left and the limit from the right are the same, I am allowed to say that the overall limit is infinity. I am also allowed to say that it does not exist because, you guessed it, infinity doesn't exist. However, if I go back to this guy, if I go back here and say that the limit as x approaches 0 of 1 over x is equal to infinity, I am wrong. because it doesn't equal infinity. They don't go to the same infinities. The only thing that I can say about the limit as x approaches 0 of 1 over x in this case is that it does not exist. So when in doubt, default to does not exist, because infinity doesn't exist. Because if you say that it's a certain infinity, or if you were even to say that it over here at 1 over x, if you were to say it was plus and minus infinity, that would be wrong as well. You can't have two values of a limit. You only get one value of a limit, an actual limit, not a left-handed or a right-handed limit. So that can get a little bit confusing, all right? So the moral of that story is if push comes to shove, say does not exist if you're afraid that you're going to make an error, okay? Okay, I think that about sums it up for today. Let's see, we got the definition of a limit, we got graphical, numerical, algebraic definitions are going to come in the next couple of sections when we get a little more advanced with this idea. Right now, all we want you thinking about as far as limits are concerned is how do they look on graphs? How can I make my fancy idiot box do what I want it to do, both graphically and numerically? You see how I sum that up in a nice tight little, let's go a second, table, yeah, which is kind of cool. And this idea of one-sided limits and how they affect the behaviors of functions and how we define vertical asymptotes. All right, that's it. Hope you enjoyed. I'll see you in the next section. Have a good day.